Hello, in this first mini lecture we are going to introduce the notion of sets and the basic operations with sets. So, sets and operations. With sets. For us, a set is nothing else than a collection of objects or elements subject to the following two rules. So the first rule is the order in which the objects or elements in the set are given does not matter. What we are meaning is that if we have the set whose elements are the letter A, letter B, and letter C, we can describe it this way or this way or this way or in any possible order that we can list these elements. Okay. And the second rule is that repeated elements are not allowed. Which means that if we have the set A, and we are supposing here that this is exactly the same object, B, C, C, for us this is the same as the set A, B, C. So repeated elements, we are not considering them. So, okay? The other important thing here is the basic notation that we are going to use for the set. Always we are going to use a curly brace to indicate where the set starts and another one to indicate where the set ends. Is that okay? And we are going to separate two different elements using a comma. Good so far? There are two basic relations with sets. When we write A and we use this symbol here, what we are meaning is, so we are going to use lowercase letters usually to stand for the elements of a set, and uppercase to stand for a set. Okay, so how do we read this? The meaning of this is A, but in general it's not necessarily the lowercase letter A. We can make reference to another abstract object is an element of the set A. Or we can say A is in the set A. Okay? Or A belongs to the set A. Okay? Alright. If you want, you can think of A as a bag in which you have objects inside. And what we are meaning here is that this is one of the objects that we have inside this bag. Is that okay? And the other basic relations here, so notice that this relation here is relating an element and a set, and this one here means that Now these two are sets, we are using capital letters, so this means that the set A is contained in the set B. Okay? Which means that if this is the set A, these are all elements in the set A, then B contains every element in A. Is that okay? If we use this little bar here, we are including that possibility in which A and B are the same set. If we remove this little bar here, well, in that case we say that A is contained in B, is included in B, but B has some extra elements. Okay? There is at least one element that is in B, but not in A. Okay? So, and we usually refer to this relation as A is a subset of B, and is when we are using this symbol here. In the case that we are using this symbol here, we are going to say that A is a proper subset of B. Okay? All right. Okay, we can also say, when we use this symbol here, that B is a superset of A. And in this case, we are going to say that B is a proper superset of A. Okay? So notice that when we use the word proper, what we are meaning is we have the inclusion, but we are removing the case in which the sets are equal. That cannot happen in the case that we have a proper subset or a proper superset. Okay? There are also some special kinds of sets. Okay, the first one is going to be the empty set. We are going to use this symbol to denote the empty set, and this is the only set that contains no element. Okay? Oh, the main property of the empty set is that the empty set is a subset of any other set. Okay? And well, it can be a little bit confusing, because if you say a set A is a subset of the set B if every element A in A is also an element in B. And you say, but the empty set doesn't have any element. How every element in the empty set is gonna be an element in B? And the problem with this construction here is that formally, this construction here is not assuming that the set A is containing elements. So colloquially, when we use all or every, we are talking about something that exists. Okay, but formally, we can be talking about something that doesn't exist. So a set that is completely empty. So when we say all my dogs with 3 heads and exactly 1 leg are green, we are not lying. Because this construction here formally is not assuming the existence of such objects. Okay? So if you want to tell me that I'm lying, you need to be able to provide a counterexample to my claim. So you need to be able to find a dog with 3 heads and exactly 1 leg that is mine and it's not green. Can you provide such a counterexample? No. So I'm not lying. In addition, I'm not claiming anywhere here that I have at least one of such dogs. Is that okay? So formally, this kind of construction is not assuming that these objects exist. Is that okay? Same situation here. When we say every element in A is also an element in B, for you to say that A is not a subset of B, you need to be able to find an element in A that is not in B. You will never be able to do that with the empty set, because since the empty set doesn't contain any element, you won't be able to find an element in the empty set that is not in any other set that you're considering. So the empty set is always a subset of whichever other set you are considering, including the empty set itself. So every set is a subset of itself. Obviously, it's not a proper subset of itself, but it's a subset of itself. So we have this property here. So the other special kind of set that we are going to consider here are the universes. So this is not a unique. It's not a unique set. Like in the case of the empty set, when we talk about the universe, is because we are talking about the set containing all possible potential objects, elements that we have in a certain situation or a certain scope. Okay, so let's say that we are creating an application that is using car brands. So in that case, our universe is going to be the set of all existing, of all possible car brands. Is that okay? Since we won't use anything that is not a car brand, that's going to be our universe. Is that okay? Well, now we are going to introduce some operations with sets. So let me give you basic example to motivate the operations with sets. Let's suppose that we have some database. I will consider all data in this database as the universe, and we are looking at one of the attributes of the data. Let's say that we have a condition, first condition, and we say, give me all data in this database satisfying condition 1. This is gonna produce a first set, let me call it A1, okay, in which we are placing all data in this universe satisfying this first condition. Let's say that also as part of our application, we are interested in those data satisfying, okay, a second condition C2, which is going to produce now a second set A2, not necessarily different from the first set A1, but possibly different. So we have two sets, maybe the same set twice. Okay? And then we want those data satisfying both conditions at the same time. So if we put both conditions at the same time, we are going to obtain a new set A3, but this set A3 is pre-related to the first two. What we have in this third set is what these two sets have in common. So somehow we are constructing a third set from the first two that we had obtained. Is that okay? Or instead of satisfying both, we can say, well, now give me all data in this database that satisfy at least one of these two conditions. And we are going to obtain now a set A4 that is also closely related to the first two. Okay? So this is what we call an operation with set. When we construct a new set from other given sets. Is that okay? And well, I will introduce my first operation. Is going to be related to this condition here. So let's suppose that U be a universe and let A and B be two subsets of U. Okay? The first operation that we are going to introduce is going to be the intersection. And we are going to use this symbol here for the intersection, A intersection B. And which are the elements that we have in the intersection? The elements in A intersection B are going to be those elements in the universe such that they are in A and at the same time they are in B. Okay? So this means that if this is the universe U, this is the set A, and this is the set B, an element here is not going to be in the intersection because it's neither in A nor in B. An element here is not in the intersection because even though it is in A, it is not in B. An element here is not in the intersection because even though it is in B, it is not in A. So the elements in the intersection are going to be the elements in this part here. Why? Because these are the elements that are in A They are in A, but they are also in B. So the intersection is going to be what these two sets have in common. Okay? Or all elements that I am. And nothing else. So, okay? So let's see an example. Let's suppose that you are all the natural numbers from 1 to 10. So the numbers that we used to count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And A is the set of or elements in the universe such that n is even. Okay? So notice that there are two ways in which we can describe a set. So we can simply list all the elements in that set. This kind of description or representation we are going to call the elements tensional. Representation of the set. Or we can provide the property that only the elements in that set satisfy. In this case, we are going to say that we are describing the set intentionally. So this is an intentional representation. And we have this universe, all natural numbers from 1 to 10. A are the elements in this universe that are even, and B is gonna be the elements in the universe such that n is equal to 6. Okay. Plus 4 for some integer number. Okay. And the main difference between natural numbers and integer numbers is, well, the natural numbers are going to be 1, 2, 3, 4, 5, the numbers that we used to count, the positive ones. And the integer numbers, in addition to the natural, are including 0 and the negative 1. So 0 is integer, but it's not natural. Negative 1 is integer, but it's not natural. Okay? So notice, for example, that 4 is an element in B. Why? Because if we choose k equals 0, we are going to get here 6 times 0 plus 4. So 4 satisfies this property here. Okay? All right. Okay. And, well, we want to find now, A intersection. So there are many ways in which we can solve this problem. Something that we can do is the following. Well, if n is equals to 6k plus 4 for some integer k, n is equals to 2 times 3k plus 2. which means that n is even. Okay? So this telling us that every element that is in B is gonna be in A. So okay? So if n is in B, then n is in A, which implies that B is a subset of A. So B is included in A. And this is telling us that what A and B have in common is going to be the whole B. So in this case, we have that A intersection B is B. So, okay? So something that we can do, another thing that we can do is the following. Well, let's say that you don't feel confident using these intentional representations of A and B. We can pass from this representation to an extensional one. So what we need to do to get the elements in A is we go over every element in U and we ask everyone, element, are you even? If the answer is yes, that's going to be an element in A, so we place it here. If the answer is no, we discard it. So 1, are you even? No, so we discard it. 2, are you even? Yes. 3, are you even? No. 4, are you even? Yes. So you continue that way and you can see that the elements in A are 2, 4, 6, and 8. And we go here and we can do the same. We already know that we have 4 there. We cannot use any negative value for K, because if we use a negative value for K, this product here is going to be negative. Is that okay? And in absolute value, bigger than 4. So this addition here is going to be negative. But in the universe, we don't have any negative numbers, so we won't have the result of applying this formula for a negative number. Is not going to produce any element in U. So negative numbers are not good for us here. So we have K0 is producing 4. We say K1 is producing 10, which is in the universe. And if we continue now increasing K, all the results are going to be bigger than 10. But 10 is the biggest elements in our universe, so other positive values of K are not producing any element in U. So B is the set whose only elements are 4 and 10. Yes, sir. And now you can say, well, what is the intersection when these two sets have in common? So 2, that is the first element in A. Are you in B? No, so 2 is not in intersection. 4, are you in A? Yes, so 4 is a common element for these two sets, so we include it. 6, are you in, 4, that is in A. Are you in B? Yes, so it's in both, it's a common element. 6, are you in B? No, so we discard it. 8, are you in B? No, so we discard it. 10, are you in B? Yes, and we can see that A intersection B is gonna be the set whose elements are 4 and 10, and again, this is exactly the set B. Is that okay? Suppose that now that U, the universe, are again natural numbers, but now we are going from 1 to 50, and A is gonna be the set whose elements are those in the universe, whose remainder in division by 4 is 3. So n is equal to 4k plus 3 for some integer. Okay. And at B, are those elements in the universe such that n is equal to s squared plus 1 for some integer s. So this means if we don't consider this plus 1 here, well, the elements that we are putting in B are the perfect squares. Is that okay? But since we have this plus 1, that means that we are taking the following to some perfect square. Okay? And again, we want to find the intersection. Find A intersection B, that is what these two sets have in common. Is that okay? Okay, well, we can notice the following. If N is in A intersection B, in particular, N is in A, but also N is in B, so N is going to be in both sets at the same time. If N is in A, this is telling us that we are going to be able to find some integer k such that N is equal to 4k plus 3 for some integer. So there is k integer, and this fancy z is the notation for the set of integer number. There is k integer such that N is equal to 4k plus 3, and we can conclude this because this is the property that every element in the set A is satisfied, and only the elements in the set A is satisfied. Okay? And if N is in B, then we can say that N is the following of some perfect square. So N is gonna be s squared plus 1 for some integer s. Okay? But if N is equal to 4k plus 3 and N is equal s squared plus 1, we can say that 4k plus 3 is equal to s squared plus 1, which is telling us that 4k plus 2 is equal to s squared. Okay? And if we look at this is telling us that s squared is even. So, because we can write this as 2k plus 1. So, s squared is a multiple of 2 because it's 2 times an integer. Listen. But if s squared is even, then s is gonna be even. Because even times even is even. Odd times odd is odd. So it's not possible that this square is even and s is odd. If s squared is even, s must be even. Yes, sir. But if s is even, that means that s is equal to times some integer cube. Yes or no? So s squared is equal 4 times q squared, which means that if a perfect square is even, it's not only even, it's a multiple of 4. Is that okay? In that case, we can come back here. S squared is not only even, s squared is a multiple of 4. But this right hand side here is telling us that s squared has remainder 2 in division by 4. So this is telling us that s squared is a multiple of 4, which means has remainder 0 in division by 4. And this is telling us that s squared has remainder 2 in division by 4. But one number cannot have remainder 0 and remainder 2 in division by 4 at the same time. So this is telling us that this is never happening. And we can conclude that A intersection B, in this case, is the empty set. They have nothing in common. Is that okay? Good so far? But well, maybe all this is a little bit complicated at this point if you are not familiar with these results about divisibility. And we can proceed in a different way. We can proceed as we did before. Instead of working with these intentional representations of the set, we can pass from the intentional representation to an extensional representation. Is that okay? Well, if we list all the elements in A, or what is the only difference from 2 elements in this set? Or the value of k that we are using. So since k is integer, again we can see the following. If we use a negative value for k, this is going to be negative, and in absolute value bigger than 3, so this is going to be negative, and we don't have any negative number in the universe, so that means that we using negative values is not producing any element in the universe, and all the elements in A are in the universe. So let's start by using 0. If we use 0, we are going to get 3. If we use 1, we are going to get 7. If we use 2, we are going to get 11. If we use 3, we are going to get 15. If we use 4, 19. 5 is going to be 23, 27. Oh, sorry. 31, 35, 39, 43, 47, plus 4 is going to be 51, but the biggest element in the universe is 50, so these are all the elements in it. Okay? Now, if we do the same for B, what we are going to get? Well, notice that S squared is producing the same value if we use either S positive so if we use values for S with the same absolute value, the sign doesn't matter here. So let's start with 0. We are going to get 1 plus 1. So this is going to be 1 plus 1 is going to be 2. I'm going to write the perfect square below, underneath. If we use S equal 1, this is going to be 1 plus 1, 2. Oh, right. We already had that. So sorry. If we use S equal 2, this is going to be 4 plus 1, 5. The perfect square is 4. If we use S equal 3, this is going to be 9 plus 1, 10. The perfect square is going to be 9. S equal 4 is going to be 16 plus 1, 17. The perfect square is going to be 16. 5 is going to be 25 plus 1, 26. 25. 6 is going to be 36 plus 1, 37. The perfect square is 36. And 7 is going to be 49 plus 1, 50. Perfect square is going to be 49. And that's it, because if we use any bigger value for S, the result is going to be greater than 15, and it's going to be outside the universe. Okay? You don't need to write the perfect squares, so I'm just writing the perfect squares here because I want to make emphasis on something that we did here. If you look at the perfect square, which are the even perfect squares? 4, 16, 36. These are the even perfect squares, yes or no? And we said here that if a perfect square is even, it's not only even, it's gonna be divisible by 4. Well, 4 is divisible by 4, okay, because 4 is 4 times 1. 16 is divisible by 4, because 16 is 4 times 4. And 36 is divisible by 4, because it's 4 times 9. So you see, this is exactly what we said here. The perfect squares are not only even, these perfect squares, these even perfect squares are also multiple forms. Okay? Well, now we have extensional representations for each of these sets, and now the only thing that we need to do is to look for those that they have in common. 3 argue here. Well, I'm going to use these ones because this set has less elements, so fewer elements. So 2, are you here? No. 5, are you here? No. 10, are you here? No. 17, are you here? No. 16, are you here? 26, are you here? No. 37, are you here? No. 50, are you here? No. So again, we are gonna conclude exactly the same thing. These 2 elements don't have anything in common, so again, the intersection is gonna be empty. When this is the case, when we have 2 sets which don't have any overlap, we are gonna say that these 2 sets are disjoint. All right, the second, again, let's suppose that U is some universe and let A be a subset of U and B another subset. The second operation is going to be the union, and this is going to be the notation that we're going to use, A union B. And what we have is the elements that we are including in the union are those elements in the union, those elements in the universe, such that, notice that these 2 symbols are pretty similar, but I'm using these little segments here for the universe and not for the union. So that are in either A or B. And be careful here because this OR is inclusive. Which means that to include an element in the union, it suffices that that element to belong to at least one of the sets. But if that element is involved, we are happy. We are going to put it there too. Okay? So, if we do this graphical representation of the union, which we call a Venn diagram, is the universe, and this is A, and this is B. Obviously, an element here, we are not putting it in the union because it is neither in A nor in B. And if an element here only in A is going to be in the union because it satisfies the first condition, an element here only in B satisfies the second condition, so it's going to be in the union, and an element here which is in both is also in the union because satisfies both conditions, but this OR is inclusive. So the union is going to be always. Okay? is the following. If you remember the intersection, the intersection with this part here are what the sets have in common. So the intersection reduces the sets. Okay? And most the sets stays as they are. Okay? But in general, keep the intersection. After intersecting two sets, every set is gonna stay the same or is gonna get reduced. But the union is the union. After taking the union of two sets, the sets are gonna get bigger, the union is gonna be bigger, or at least stay, the set is gonna stay as it is. So we have the following remarks here. For any set we have, for any two sets, A intersection B is gonna be always a subset of A, obviously. It's gonna be a subset of B too, but A is gonna be a subset of the union. Obviously, this is also valid for B. Okay, so if we have A and we take the intersection with B, either the intersection is gonna be equal to A or the intersection is gonna be smaller. If we get the union with B, either the union is going to be equal to A or the union is going to be bigger. But never the union is smaller than A, never the intersection is going to be bigger than A. And never they have these inclusions are not valid. Is that okay? So let's see some examples. Let U be the set of rational numbers, and the set of rational numbers are those that we can write as a fraction of integer numbers. So those that we can write as P over Q, such that P is an integer, and I won't write and when I'm describing, when the property that we are using is, let's say, a compound property, I will use comma to separate everything that needs to be satisfied. Q is also an integer number, and obviously Q must be different from zero. Is that okay? Is that good? And let's consider A as the set of those elements I will use N in the universe, such that N is equal to 1 plus 1 over N for some 1 plus 1 over K for some integer K. All right, and let B be the set. Whose elements are those elements in the universe, such that N is equals to 1 minus 1 over K. I put different 1 over S for some integers. Okay, and now we want to find A union B. Okay? Well, in this case, we are gonna include that element in the union if it's either in A or in B. If it's in both, we are including them. Oh, well, it's pretty easy to verify that what is going to be the intersection of these two sets. Well, if we put here some positive integer and positive integer, if we reduce the set of integers to the positive one, natural numbers, well, in this case, the intersection is going to be empty. Okay? Why? Because if k, for some integer k, not q. If k is positive, 1 over k is going to be also positive, so we are going to be adding something to 1. So every element in A is going to be bigger than 1. If S is positive, in this case we are going to be subtracting something from 1. And the result here is going to be always less than 1. So all elements in A, in the case in we are considering only positive integers, are going to be bigger than 1. The elements in B, all of them are going to be less than 1. So obviously in that case they have nothing common. But we are not considering that case. We haven't restricted the integers that we are using. So okay. So you can see that the intersection of A and B is going to be equal to A, but also equal to B, because these two sets are exactly the same. Yes or no? Well, let's see that. If N is in A, then N is equal to 1 plus 1 over K for some integer K. Yes, sir. Let's take now S equals to minus K. If S is equal to minus K, N is equal to 1 minus 1 over minus K. Yes or no? Is that good? Let me do it this way. I want to put it this way. 1 plus 1 over K is the same as 1 minus 1 over K, which is the same as 1 minus 1 over minus K. But minus K is S, so this is 1 minus 1 over S, which is telling us that N is also in B. So if N is in A, N is in B. But this is telling us that A is included in B, so maybe B has some extra elements, but obviously we can repeat this. Exactly using the same argument, we can see that every element that is in B is going to be also in A. So this is telling us B is also included in A. If A is included in B and B is included in A, B cannot have anything extra, so the only possibility that we have is that the two sets are the same. Indeed, this is a technique that we use when we want to prove that two sets are equal. standard technique is we prove a double inclusion. So, okay? Plus, let me do it. If we suppose now that n is in B, then n is equal 1 minus 1 over s for some integer s. And we can take now k, is that okay? As minus s. Okay? So here we are going to have 1 minus 1 over s is equal to 1 plus minus 1 over s, which is equal to 1 plus 1 over negative s equals to 1 plus 1 over k. So, okay? So, this is telling us that these two sets are the same. If these two sets are the same, the union is gonna be equal A equal B. If you think of this as follows. So we have A. What is B doing when we take the union? B is bringing new elements, yes or no? Or at least A is gonna stay as it is. But B is bringing new elements if B has some element that is not in A, but every element that is in B is also in A. So B is not contributing with anything new. So when we take the union with B, since everything that B has, we already had it in A, that union is not changing A. The same thing if we start with B. All the elements in B, when we take the union with A is gonna bring new elements if A has some element that is not in B, or at least B is gonna stay as it is. But in this case, all the elements in A are also in B, so when we take the union, B stays as it is. Is that okay? Well, this is an example also in which passing to the extension and representation is not that easy because we have infinite elements in both sets. And what you can see is the following. We have 1 here. Obviously, we cannot use k equals 0. I don't need to put that here because simply the formula is avoiding that value for k. I say, oh, k1, we are going to get 2. All right? k2, this is 1 plus 1 half. k3, 1 plus 1 third. k4, 1 plus 1 fourth. So what we are going to do is, when we increase k, this term here is getting smaller, so the elements that we are obtaining are going to be closer to 1. But if you go here, and instead of using the positive values, you use the negative, you say s equal negative 1, f s equal negative 1. This is negative 1, but 1 minus minus 1 is going to be 2 again. Is that okay? S equal negative 2 is going to be 1 minus minus 1 over 2. That is 1 plus 1 over 2. So we are going to get this value. And so on. Yes, sir? So the value that we obtain here, the value for n that we obtain here using a positive value of k is going to be the same value that we obtain here using the opposite of that value. Is that okay? And vice versa. Because if you start using here a negative value, what you're going to do? Well, k equals negative 1. That's going to be 0. K equals negative 2. This is 1 minus 1 over 2. So we are going to be here. 1 minus 1 over 3 if k is 3. And we continue. So again, we are going to be approaching 1 as k goes to negative infinity, but now approaching 1 from below, from lower values. Is that okay? And again, the values that we are obtaining here using negative values for k are the same that we are going to obtain here using positive values for k, for s. Is that okay? So in this case, these are the same set, so the union is going to be equals to both of them, because they are the same, right? Okay, well, the next operation that we are going to introduce is the complement. So the two previous operations were binary operations, which means that we use two sets to operate with, but the complement only needs one set. So again, U is the universe, okay, and A is a subset of U. So the complement of U, and I will use this notation, but there are many classic notations. I will use this one here, is those elements in the universe such that it is not in it. Okay? So if we do a Venn diagram for this, if this is A, the complement is gonna be on this. So obviously, since an element cannot be in A and outside A at the same time, a basic property here is that A intersection A complement is empty. So this means that A and A complement are disjunct. So let's see this example here. If we take again U as the natural numbers from 1 to 10 and A as the set of the even elements of the universe, which we can also describe extensionally as 2, 4, 6, 8, 10, then we can see that A complement are gonna be the elements in U that are not in A, but since a natural number is either even or odd, the ones that are not even are odd, so the complement are gonna be the odd ones, and if we use an extension representation for the complement, we are gonna get that the elements of the complement are 1, 3, 5, 7, and 9. Is that okay? Okay, the next operation is gonna be the difference. Okay. We will use this notation, A difference B. Okay. And what we have are that the elements in the difference are those elements in the universe such that they are in A but not in B and not in B. Okay? So these two points here, we are going to read them as such that. So the elements in the universe such that they satisfy the condition at the same time the second condition. Okay? Well, what we have to do if we want to compute the difference of two sets is we go over the elements in A and we ask every one of them, are you in B? If the answer is yes, we discard that element because we are just keeping the elements in A that are not in B. So, my friend, are you in B? Yes. Go away. No, we keep it. Okay? So, for example, if the universe is, again, the elements, the natural numbers from 1 to 10, and A is equal to the even numbers, and B in the universe, B are the odd numbers. In the universe, A minus B is gonna be A. Okay? Because for every even number, when we ask it, are you in B? Since that number is even, it's not gonna be in B, because the condition that a number needs to satisfy to be in B is that that number needs to be odd. So the answer for every element in A is gonna be no. If it's in A and never in B, we are gonna keep it, so we are gonna keep all the elements in A. And obviously, we can write here, we can list all the elements in A, have 2, 4, 6, 8, and 10. All the elements in B, 1, 3, 5, 7, 9. So, if we ask 2, are you in B? The answer is going to be no, so we are going to keep it. 4, are you in B? The answer is no, so we keep it. 6, are you in B? The answer is no, so we keep it. The same for 8 and the same for 10. So we are keeping all of them. A minus B in this case is going to be, we are keeping 2, we are keeping 4, 6, 8, 10. Which is 8. Okay? But if we, instead of B, we consider another set C, that are those elements in the universe such that they are a multiple of 4, then we are going to have the following. Oh, and now we want to compute A minus C. We have the following. Well, every multiple of 4 is even, because we can write this as 2 times 2k. So every multiple of 4 is also multiple of 2. And now we need to repeat the same procedure. We need to go over the elements in A, and we need to discard those that are in C. Well, which are the elements in C? Again, if k is negative, this is going to be negative, but in the universe, we are not considering any negative number. So, we need to use 0 or positive. If k is 0, we are going to get 4. If k is, if k is 0, we are going to get 0, That is not in the universe either. So k1, we are going to get 4. K2, we are going to get 8. K3, we are going to get 12, but 12 is not in the universe. And if we continue increasing the value of k, their formula is going to produce an element that is not in the universe, so it's not going to be in C. So this is an extensional representation for C. So now we go to A. 2, are you in C? No, so we keep 2. 4, are you in C? Yes, so we discard it. 6, are you in C? No, so we keep it. 8, are you in C? Yes, so we discard it. 10, are you in C? No, so we keep it. And this is going to be A different C in this case. Is that okay? Something else that we can notice is, if we look at this expression here, is the following. If it's in A and not in B, well, not in B means that, this means that else is in A. This means that else is, if it's not in B, it has to be in the complement of B. So this statement here can be rewritten this way, but if X is in A and in the complement of B, that means that is in the intersection of these two sets. So one property that we have here is that taking A difference B is the same as taking A intersection B complement. So here we have two different sequences of operations that are producing the same result. Okay? And another important thing here is that A minus B in general is not producing the same result as B minus A. So this operation here is not commutative. We didn't say anything about that for the intersection and the union, but you can verify easily that both intersection and union the results are independent of in which order we are taking the sets. But here, for example, if we take C minus A, well, the only elements in C are 4 and 8. 4, are you in A? Yes, so we discard it. 8, are you in A? Yes, we discard it. And C minus A is going to be empty, which is different from A minus C. So we have these two interesting properties for the difference. And that's going to be all for